This problem reads, in each of the following cases, what element does the symbol X represent and how many neutrons are in the nucleus? Use the periodic table as needed. Okay, so 195, 78, X, I'm going to look up the 78 because that's going to tell me a number of protons in the nucleus. And let's see, that one would be, where'd it go? Right there, platinum with 78 protons. And then here's the mass number. The 195 over here means the number of neutrons and protons combined, which means that in this particular isotope there are 117 neutrons. You subtract the two numbers. So yeah, 117 neutrons, 78 protons, and the element is platinum. The reason that the mass number itself is not an integer, well, there are two reasons, is that there are a number of isotopes for platinum, so there might be platinum 195 or 196, 198, 192, and so that's kind of an average. Plus, there is also binding energy involved that reduces the average mass number. Alright, so this one here is platinum. Let's see, 16 protons. I can see that over here. There's sulfur, and then of course 16 neutrons as I subtract the two numbers. Alright, 29, let's see, there it is, copper, and 29 protons for the copper and 34 neutrons. 5, there it is, boron, 5 protons and 6 neutrons in this isotope. Here for boron, it's almost easy to see the ratio between the predominant isotopes. There is apparently 80% of boron is made up of boron 11 and 20% is made up of boron 10, and then when you put them together you come up with 10.8 on the average for the mass number. Okay, and the last one here, the 94, let's see if I can see it there, it's right there, plutonium, so 94 protons, and then 239, that's a different isotope than from what the average mass number is, so 145 neutrons for the plutonium. Let's see if that is Pu. Yes. Okay, even though I'm already done with the problem, I figured I might as well look up specific isotopes, for example, for platinum. This Web Elements web page, which is in England, is really good. It's probably the premier chemistry website. So here are the naturally occurring isotopes. Notice that there's platinum 190, 192, 94, 95, 96, 98. The numbers I mentioned earlier, they were just top of my head. I just made up a few numbers. And here we can see how much percentage out of 100% each one of these takes on. Apparently 195 is the largest one, with 194 right behind it, and that's why we get, and then actually 196 pretty close as well. That's why we get kind of an average of 195. The ones that you don't see here, the 191 to 193, must have such a low, small half-life that they're not naturally occurring. I'm going to click on boron here, and as I mentioned, as I was looking at the average, I'm sorry, at the atomic mass, which is the average between, or the weighted average between the different isotopes, I guessed correctly that 80% is boron 11 and 20% is boron 10, making for 10.8. By the way, if we look at, let's see, I wanted to look at chlorine. How do I get there in the best way? I think I'm just going to click on there. Chlorine, notice here 35.4, kind of, we could guess that, well, probably like A little more than half of it is chlorine 35, and a little bit less than half is chlorine 36, makes for 35.45 on average. But look what happens, a little bit different. Sometimes you can guess at it and sometimes you can't. So it turns out that chlorine 35 is 75%, and actually chlorine 37 is about 25%, and that makes for a weighted average of 34.5 almost. This problem reads, use the binding energy per nucleon curve to determine the total binding energy of oxygen 16. And this one is really going to be easy. Here's the oxygen 16, 8 protons, 8 neutrons, makes for a total of 16 nucleons. And per nucleon it has a binding energy of 8 mega electron volts. So the total binding energy for that particular isotope is going to be 16 nucleons times 8 mega electron volts per nucleon, and that is going to be a total of 128 mega electron volts done. But of course I want to do a little bit more here, and that is that I'm going to look at what happened with this binding energy. It would have to be equivalent to a certain mass deficit, where E equals the mass deficit times c squared. So I'm going to determine this one here in a moment. Let me look first at oxygen 16 on web elements, and I'm going to write this number down here, that the atomic mass of oxygen 16 is 15.9949. I think I'm going to truncate it here. Atomic mass units. It says atomic mass, so that includes the 8 protons for the oxygen, the 8 neutrons inside that isotope, and the 8 electrons that are orbiting the nucleus. Okay, and then I don't know what happened with my smartboard software. There it is. So I'm going to write that one down. 15.9949 atomic mass units. Okay, now I'm going to look into it that I got in 1608. I got 8 protons and 8 neutrons and 8 electrons, and I'm going to see how much mass that is in atomic mass units. So I'm going to grab the calculator, and for the neutron I'm going to calculate an atomic mass of 1.674927. It's almost an overkill. Times 10 to the negative 27 divided by the atomic mass unit itself, 1.6605. Trying to find it here in the book. 05 times 10 to the negative 27, and because both of them take on the same exponent, that's why I can leave it off. So the neutron has a mass of 1.008688, and this is where I'm going to truncate that. So I'm going to write that one down. Probably need more space. So 1.008688. That's for the neutrons. Then I could show you the calculation for the proton, respectively. I did that on the side. So for the protons, I have 1.007300 as I divided those numbers, and those are also in, these are all in atomic mass units. I'm just writing neutron, proton back here. And then for the electron, 0.000549. Why does the neutron have a larger mass than the proton? Well, the neutron, if it's left by itself, if it's not bound in the nucleus, is able to decay with a half-life of 15 minutes, is able to decay into a proton and electron. And if you look here at the masses here, then you see it has to have a higher mass as the proton. The proton is not able to do that. The proton is not able to decay by itself into a neutron because it wouldn't have enough mass. Notice that it actually has more mass than the proton and electron combined. In any case, these are the masses for the three elementary particles, and in the oxygen, each of these here is going to appear 8 times. So I'm going to add these up, multiply by 8, and again I did that on the side, and I come up with 16.132 atomic mass units. I write this here to 4 decimals or 6 significant figures, because here I also did the same thing. Notice that if I combine 8 neutrons, 8 protons, 8 electrons, I come up with a larger mass than the oxygen 16 isotope has. So if these 24 elementary particles combine, then what happens with the mass here? Well, this is where the rest mass comes in. So I'm going to do that calculation. So I'm going to take the 128 mega electron volts, and first I'm going to change that. Hold on one moment. Change that into joules. So 128 mega electron volts, which of course 128 times 10 to the 6th times 1.602 10 to the negative 19. Okay, so that's how much joules is used in binding energy. Then I divide by c squared to get the mass deficit. And let's see if that's correct here. Speed of light. Looking up in the book, where it go? Yep, that's right. Times 10 to the 8th meters per second. Square that. There we go. That's the mass deficit in kilograms. Divide that number by 1 MAU. So 1.6605 10 to the negative 27. And come up with a mass deficit of 0.1374 atomic mass units. So delta M, let's see if I can still use another color here. So delta M, trying to write an M, equals 0.1374 astronomical and atomic mass units. Goodness. And I think I'm going to put the U here. Atomic mass units. And now I subtract these two from each other. After all, it's called the mass deficit. And when I do that, let's see, one moment. .16 0.1323 minus 0.1374. And there we go. Oh, right on. 15.9949 astronomical mass units. So what happens is that this is the mass of 8 neutrons, 8 protons, 8 electrons combined. When I combine them, I get oxygen 16, but the total mass is less than that by this much, and that mass deficit is used for the binding energy to keep the nucleus together.